All right, irreducibility. What is that? Yeah, maybe I should have that come in order, huh? The linear factorization theorem just told us how many total factors there are, but you may be asked to factor it completely, or you might be asked to factor it irreducible over the rationals or irreducible over the reals. Irreducible means that it cannot be factored any further. So if they say irreducible over the rationals, that means there are no other rationals that can be factored out of it. It sounds a lot more complicated than it is. Okay, the rational zero procedure will give you the factors that are irreducible over the rationals. Factoring, or the quadratic formula, will give you your factors irreducible over the reals. Factoring in and of itself, or using the quadratic formula, will give you the complete factorization. All right, so the only way to understand this is through some examples. So here we have a fourth degree polynomial. We would start with our list using the rational zero test, all the factors of 30 over all the factors of 1. And you'd get a lot. You get 1, 2, 3, 5, 6, 10, 15, 30. All right, so rather than doing a bunch of trial and error and stuff, I'm just going to go right to it. Okay, it's divided by 3. Okay, 3 is one of our rational zeros. I'm going to keep going. This time we'll try -2. Why -2? Because I just happen to know it works. We don't have time to watch Mr. Wenta go through trial and error. We want to get to the bottom of what irreducible means. There we go. Our second rational zero is -2. All right, now if you look at what remains, that's basically x squared minus 5. All right, so that's going to give me plus or minus the square root of 5. Those are all the zeros. All right, so I'm going to show you how you would factor this according to the irreducible rules. All right, the first set was rational, the second was irrational but real. So if I'm asked to factor it irreducible over the rationals, okay, that means I separate each rational factor and I leave the rest like that. If I am asked to make it irreducible over the reals, okay, then I'm going to take this right here and I'm going to break it up into x plus square root of 5, x minus square root of 5. All right. Now, because there are no imaginary solutions, this is also my complete factorization. All right, because there's no imaginaries, there's no difference between irreducible over the reals and factored completely. All right, so it's not adding any work to what you've already done. We go through and we try to find all the possible zeros, and this is just how we're going to express our answers. Okay, the reason we might want to make that differentiation is because you can look at this term and this term and say, oh, I know it crosses at x equals 3 and that x equals -2. All right, great. So I know it crosses there, no, it crosses there, and I know that that doesn't mean, well, actually that does. It means plus or minus square root of 5. Square root of 5, oh heck, I don't even know what that is in my head. But they're not whole numbers. Somewhere, I don't know, right here, right here. It's fourth degree. It's going to be going upwards on both sides, so it's going to look something like this. Woohoo. Yes. Let's try another. All right. So we have all the factors of 26 over all the factors of 1. There are not many factors of 26. That means finding the rational should be pretty smooth. Let's try 1. What do you want to bet this one works? I wouldn't put you through trial and error, would I? We've been there, done that. Okay, 1 is one of our answers. What else? Let's try 2. Yeah, that's a bit of a mistake right there. This should be 26, not 10. Don't know where the 10 came from, but that gives us another rational 0. And now we have to see if that's factorable. Ooh, it's not. We got to use the quadratic. Oh, and not only is it not rational, it's not even real, man. So we have those rationals, those imaginaries. So if I want to factor it, irreducible over the rationals, and in this case the reals, because I didn't have any square roots. Okay, remember, rationals can be written as a fraction. They don't have any square roots in them. When I'm talking about reals, reals have square roots in them. Imaginaries have i's in them. All right, and completely factored would look like, that's not right. Gonna have to go make some adjustments here. This should be x minus 2 plus 3i, and this should be x minus 2 minus 3i. There. So hopefully you guys understand the difference between irreducible over the rationals, the reals, and factor completely. Because that's the end of this video.